So the title of my presentation, from silicium layouts to circuit diagram. We normally look at integrated circuits as black boxes. We can download data sheets from the manufacturers, but we never get a circuit drawing from the manufacturer. So then we have to use a microscope. A very old 8-bit microprocessor, 6502, is what I use to demonstrate what results you can get. My presentation consists of three very well separated parts. 6502, why you should look at it with a microscope, and what are the motivation behind those who use a microphone for integrated circuits. Most of you in the audience are IT experts, and a lot of words are going to be about transistors in this presentation, so I'm trying to make it simple rather than scientifically precise. At the end of my presentation, I'm going to show you how these simple transistor links look like on the silicon surface. So what is the motivation for using a microscope to see an integrated circuit? One is the breaking the code protection on microcontrollers. Protecting software is quite hopeless. There are cracked versions of software all over the internet. This is not true for microcontroller environment. There is very good hardware protection to keep the code in a single chip in the computer, which includes a CPU, program store, operative store, and all sorts of operative storages. If you put in a code, it works the same way, but from the outside you cannot read the code. And in a microcontroller, using an electron microscope, you can sort of flip the code protection flag. The second is the resolving documentation problems. Obviously, if you have a chip which is not working and you would like to improve the driver, or you would like to revive an old hardware, then a circuit diagram comes very well. And then also you may have educational targets if you use microscope for integrated circuits. For instance, an engineering student learns a lot about 10 or 20 transistor links, and then you can build them up very well to design processors later on. But while an IT expert can look into a lot of professional projects, an engineer only has access to Verilog and VHT sources, which is relatively a high-level description of the hardware, but it's not a real layout. Why 6502? Approximately 10 years ago, when I was in the position to check an integrated circuit under the microscope, I selected 6502. It's quite an old technology, 6 microns. Microns to chip width, and with an optical microscope, the limit is 1 micron, so the 6 micron makes it easily available for investigation. This processor is typically known from the Commodore era. There is a generation in Hungary as well whose first experience came from the use of Commodore 64, and I was always interested in code protection mechanisms and tricks. And one such thing was non-documented codes, or that is forbidden codes. So if you use non-documented codes to write the deciphering code for your chip, then you could hide it from hackers. Now, the reason that I selected this processor for reverse engineering, I was looking for the rationale why they planned a processor which has well-documented and also non-documented operations. So I had to obtain a test copy and take take the cover off, for which I used acid. And after flushing, I put the chip under the electron microscope, and on the right hand side you can see a picture of the electron microscope. It's a grayscale picture, there's no color information, but it's quite good 3D image. However, I could not find transistors in it, so I switched to an optical microscope, which is on the left hand side. This could be in color, but the university equipment was not able to produce color picture, but nevertheless grayscale was good enough. And here you can see these black lines which do not appear at all on the electron microscopic image, which are very important to decipher the circuit. First, I had to solve a joining problem. I had a CCD camera for the microscope for 512 by 512 pixel pictures, and I had to cover the entire layout so that I could see all the lines and transistors. Without zooming into this picture, you have an overview, and there are three major areas. This is the register block. Here you can see immediately that it's an 8-bit processor. Roughly you have 8 columns, and the registers are aligned horizontally. On the right hand side you have a well-ordered structure. This is basically a table and a ROM helping the commands or the instructions. And here we control the data flow in the register block. Silicium layout can be very different, varied. You can have the same connections drawn in several different ways, and in order to see the principle of order in such a mass, you need graphic rules. So if you look into a dentist Röntgen X-ray picture, you may not make sense of it. Once I asked my dentist, could you show why, how do you know that I have problem with that tooth? Well, he said, very simple, look at it, there are those black dots on your tooth there, and those are the problem. Now I saw the black dots, but I saw black dots all over on my other teeth as well, so I still don't know the graphic rules for X-ray images. After 2 or 3 weeks of studying, I managed to grasp the graphical rules of silicium layers to find the transistors. Deciphering was mostly paperwork. I printed the entire layout on A4 sheets, and when I found transistor, I marked it and marked the connections, and once covering the entire layout, I had a very complicated graph. And then I discovered that the whole thing is bad after all, because I marked conduits that had the same information flowing but not in the same phase. Then after all, finally I managed to get the final drawing, which took me about 1 month, and then I had the circuit diagram completed roughly like that, with the similar functions grouped together so that you could roughly see what is happening there. Others solved the very same problem another way. In the past 10 years, quite a lot of people contacted me from abroad. Those who did not really work with this processor, they did exactly the same job as I did. we just used a little more advanced methods because they worked lately, and when on top of that they even wrote a web simulator, the point of which is that while you're looking at the binary code on the layout picture, you could see the wires or conduits that are active because they are marked in different colors. Now from here on we're going to talk about transistors for the most part. So let's take a look at this water analogy. So if you substitute water drops for electrons, electric power is water flow, amperage is flow, voltage is water level, resistor is reducer. The most important element is the transistor, because in a processor you mostly have transistors and conduits. So if I'm not entirely precise, just want to make sense, it's a 3-electrode device, and on one I can determine whether there could be a flow of electricity power between the other two. This is a mechanical device. On one outlet I can determine whether the other two may have a flow. So it's like a water tap. An open transistor is just like an open water tap. Even if it's open, the flow will continue only there if there is feed from behind. And if I use another example, if I fill a capacitor and then I charge it and I get electricity, it's like filling up a tank with water, and when I discharge the tank then I get the water flow. So this analogy stays. Inverter is one of the most frequent parts of these. Logically, there is a logical zero for at the input and 1, and then the other way around. This is the most frequent part of it, and it's not because inverting as a logical operation is needed so much, but we like inverters for other reasons, like we can delay signals, we can build oscillators, time signal generators, clock signals, we can use it for signal generation. We can regard it as a 1.5 volt can be regarded as a logical 0 volt, like 0 volt, but we can put them in order with a even number inverter. High current drive can be solved, but there are microamperes within the processor inside. But as we go outside of it, so for instance when a memory wants to communicate with memory, with the conduits that you can actually see, then there are big power amperes, and then building buffers is another thing that you can use inverters for. Cross-linking inverters can be used for building storage. Now, how does our water inverter work if you build it in a CMOS-like manner? We have 2 tanks, an input tank and an output tank, and there are walls in between. The walls are alike, but they are installed the opposite way. There is a joint rod, but when one is open, the other is closed, and vice versa. Now, if there is a logical 0, because there is low water level at the input side, then the lower one closes and the upper one opens. And from the water feed, it fills up the output tank to the logical 0 level. If it were high water level on the input tank, that would open the lower valve, let the output tank discharge, and so forth. So the inverter works in a water manner. A real transistor inverter is built in a very similar way. You see the CMOS transmitter on the right hand side. drain, source, gate are the names, but it's enough to memorize gate, and the gate will decide whether there can be a flow between drain and source. And CMOS inverters basically works in such a way that the input is connected to the gates of both transistors. N and P substitutes for the inverted valves. So if input is logical 1, then N opens and P closes, and over the open N, output is grounded, like a closed circuit. So to logical 0, the answer is logical 1. And the invert is true, so in that case N closes, P opens, and 0 to 1. So it works the very same way as in case of the water inverter. This is the NAND gate. You have to understand that there are no AND gates, but you have NAND gates, non-AND gates. That is to say, it works, it only sounds complicated for the first time, but it's easy to get accustomed to. Now, with the water supply, you get A and B valves. You have the output tank. I didn't put on the input tank, but you have A and B for the two valves. They are invertly installed. Now, when the A and B valves are open, then you can discharge output tank to 0. 0, 1, 0, 0. Case you cannot discharge the output, but a valve opens on the top and fills up the output to 1. This is the same thing in the transistor. You have two N transistors down and two P transistors upstairs. If A and B transistors are open and grounded, then you can have it to 0. The NOR gate works very similarly. You should realize why this is. Why is it MOS? Because it consists of MOS transistors, and C because the transistors are connected in a complementary manner. So what is parallel down there is serially connected up there. In case of the NOR gate, either A or B is 1, then we can drain the output tank to 0. Otherwise, this is filled up to 1 through the two valves upstairs, and the transistor equivalent is there. Now that was on the side, because this old processor is not CMOS but NMOS, but I should mention the difference between CMOS and NMOS. NMOS is a much older technology. It uses only N-type transistors. And the water analogy is interesting because you can use a single valve, and you only need a narrow pipe section in there. So if it's 0, logical 0, then the drain closes, the valve closes, and then you fill up the output tank to 1. If it's logical 1, the valve opens, which has a greater flow than the narrow pipe, so we can nevertheless drain the output pipe in spite of the fact that the water supply still comes, water feed still comes. It takes a lot of water, of course, and it takes a lot of power in the electrical solution. Now the transistor version you can see on the right side, and here you should have a resistor, but rather we don't put a resistance in a processor, but you use a transistor. Basically it works like for logical 0, the transistor opens and brings it to 0, and otherwise it's connected to switch power feed to feed. We can leave the water analogy now. It's very easy to tell from an NMOS gate what logical function belongs to it. So what we have to see that the X output, what is the case to bring it to 0? if you have a mount gate on the left hand side, we have to have A and B open in order to bring X to 0. So it's negated both N and both B, and in the right hand case you can bring X to ground if A or B and negate it, because all gates are negated.
Akár egy komplex kapunál is.
So even in the case of a complex gate, this is a rather simple logical equation. You can see that 0 is the output if the E and B, C and D, or F and G, or H. And we negate that because all of them are gate output. A transfer gate is a tool that can provide or hinder a transfer of information. And depending on the actual operational code, which one of the transfer gates that receives a logical 1 on the input and sends that to further processing. The further processing is an inverter, but there are other things happening as well. And this is the 1-bit storage. This is 2 cross-connected inverter. We could call this the saved data X, that is attached to another input of the other inverter. It goes back and stays as an X. So it's a 4 transistor storage, even that is not bothered with a clock signal. And in order to organize a bigger memory from this cell, we need 2 transfer gates. We can address those couple of cells that we want to read or write, and to do some calculation. Let's see how many transistors do we need. 48 for 1 byte, and to 128 kilobytes we need several millions of transistors. Now, of course, we can do that in the Commodore time. This has less than 4,000 transistors, of course, cache not included. This is the most complex gate in this structure. You need to understand that these in the middle, these 2 gates, are also cross-connected, not inverters but gates. So they store 1 bit. This is an inverter on the left side. Then it's a through a transfer gate, but double inverter, logical nothing, goes to the complex gate, and it goes back to the left side inverter. And the storage had to be complex because it not only stores at 1 bit, but it also has an increaser. So it just calculates the number of operations of processor. So it always adds another, and the overflow bit comes up here. This is a section of command decoder. You can see the operating code comes in, a couple of inverters, transfer gates, and goes into the command register. 1 bit storage here. We needed transfer bits because we don't have to input each and every bit, because we also have operandi that's not allowed to go into it. And here in one cell, either you have a transistor or not. What happened here is the engineers saved 1% of silicium surface, and that's why in this processor there are non-documented operating codes as well. So this is the layout. You can see the cross-section of a transistor on the left side. Unfortunately, we don't have time to go into details, but it is a one crystal silicium. It's contaminated and changed the conduction conditions. So basically this is a three-dimensional structure with several layers, but there's only one transistor layer, and this is called active zone. From here to there, between the two N pluses, there is current when the gate source opens the transistor. This is how it looks under the optical microscope. You can see the end of the active zone, and this is a silicium band. This is a gate. This is a transistor, and current can flow between the two when we open the transistor. And we add aluminium to it. You can see that it's on top of the sandwich structure. In this processor, there's only one metal layer. And since aluminium is on top of the structure, it can be laid over a transistor without tampering. And if you need to connect it to the transistor, then you do this, connect aluminium to the N plus zone. These are all the components. We already discussed active zone. This is the black mark on the gray background. This is the boundary of the active zone. Active zone has double fold dust. First of all, it could be used for wiring, and also it makes a transistor if the polysilicon line crosses it. It also has a double task. It could be used for a line, or if crosses an active zone, then it's a transistor gate. We already seen the aluminium. That is that material here. It is only used for wiring. We can connect aluminium to the active zone, so these are 4 contacts here. And there's another contact, a hidden one, or a buried one, and this is connecting the polysilicon with the active zone. That's a buried contact. This is also a layout made with Photoshop. You can see 4 transistors here. But what you need to know is the W/L ratio. You can see this. The left side is smaller, the second one is bigger, this is even bigger, and on the right side, this handles less current because the gate is twice as thick. Is it good for anything? Yes. As we use the water analogy, you can see that here this is basically a bottleneck. So this is this which is the power. The borderline is as having a similar color on both sides, so we can't tell which one is the active zone. On the right side you can see an active zone with a polysilicon band, so left side is nothing, the right side is a transistor. What is important that this polysilicon is crossing the borderline. And the reason for that is that we of course cannot produce twice the same, so there is certain manufacturing tolerance. Same applies to microelectronics. So if this band is shifted to the right, then it will not reach the borderline, and then it will be a faulty transistor. So this effective layout on the right side, you can never see that on the microscope. So we need a gate overflow. So the active zone is always on the other side. I just added some aluminium foil to that. If we see something like this is definitely not an active zone, but the E is the active zone, which means that there is no active zone on that side, so there is only a C polysilicon that is contacting the F aluminium. On the right side you can see two active zone borderlines. That's separate this layout into three parts, and this is the active zone, so that's a transistor, which means that neither this, neither that is an active zone. But we have an aluminium wire crossing, and there is also a contact to the F. So there is only one transistor here. And this is a real layout. We'll try to identify the circuit here. First of all, we have to identify the active zone. It has a rather complex shape, where you can see that. And we know that there is an active zone because we can see the gate passing the borderline, so no, this is the active zone. And we see that this is an active zone here. There are three polysilicon bands, 1, 2, 3, meaning that in this layout we have three transistors. And that transistor here has double bandwidth, so that it has to be the power switching transistor, which means that this band here is a power supply, but it also has to have a ground somewhere, meaning that this aluminium foil is the ground. And we can see that there are 3 contacts to the active zone. So we already identified one of the transistors, and let's look at the input. You can see that we have, through a transistor, the input is grounded, and the gate of this transistor connected to the ground through that buried contact. So that's an input and a closed transistor. The closed transistor doesn't change anything in the logic, so basically this is an ESD protection. So we are not bothered by it. We just go forward in an active zone, and we see another buried contact. We've seen that already, that is a transistor. On the 2 banks there's a output and the ground, so this is the 3 transistor circuit, and that's an inverter. The second example could seem very chaotic. This is not a borderline, this is the border of the picture, but this long one is basically one line, so most probably this is only one transistor on the left side, and I mentioned W/L ratio, so this is basically a folded transistor. This black dot is basically a very thin golden wire. And the second transistor, and this is also a folded transistor, switching power on the output. So if we see something like that in the silicium, everything will be very well identified. Now this is a rather complex layout. We cannot use the active zone because we have so many active zone borderlines that it's very easy to get lost. At least 4, 5, 6 active zones that I can count here. So first I will look for the transistors with double width, so we know that this aluminium wire is the power. We also see here loading transistors, so this is also power. We also have aluminium wires that are not connected at all, so there is passing by. Then going further up I can see a buried connector. It's not easy to recognize, but there is an aluminium foil above it, so which means that there is an active zone, and there is a polysilicon silicium, and I know that this is a ground, so I would say that these should be the homework for you, and I'm about to complete my presentation. And if you're interested, then you can download my presentation from the Hacktivity website, and you have all the relevant tool for identifying this layout. So I wish you great success. I hope that you will succeed, and thank you very much for your attention.